All right, so this week we're going to finish up the arrays and the collections in Java in anticipation of next week, because there's no Monday or Tuesday exam, like there's no class and no lab next week. Instead, we're going to, again, finish up arrays and talk a little bit about tooling next week. Or this week, we'll introduce you to a couple of debuggers. And then Wednesday of next week, we'll use that class time as a review, same as last time. I'll bring last year's exam 2 and we'll do it. If we have time, we'll do 2 years ago exam. And it'll be the same format as before. You'll have 24 hours on that Friday. So Friday the 28th, is it? No, sorry, the 25th, right? Friday the 25th, we won't have class. You'll have 24 hours to submit it. Same exact format as before. It will cover everything up to and including arrays, so keep that in mind. So we spent a lot of time doing some exercises and making functions that use arrays, that return arrays, et cetera, et cetera. Just to review, the memory management that we talked about, because it has been a little bit. Once you're done with a chunk of memory, remember that you need to give it back. This is now C in the context of C here. Because if you don't give it back, you'll have what's called a memory leak. And you're going to witness this firsthand tomorrow when you'll be using a tool called Valgrind. Valgrind is a dynamic analysis tool that can monitor your program and say, oh, you've got a memory leak here because there was memory allocated on this line and it was never released. So you go back in and you fix it, right? Otherwise, you'll have a memory leak, right? To give memory back, we use that function called free, right? Once you free it, of course, you cannot access it, right? In fact, you should not be able to access it because it's now memory that doesn't necessarily belong to your program. It could have been given away to another program. It could have been reallocated to your program. It could have just been corrupted, right? You cannot and should not free memory twice. We saw that as well. That's a double free event where you free something, well, it doesn't belong to you, so you can't free it again. And that can either manifest itself as a double free fault or a segmentation fault of some sort. But this all goes to the question of who actually owns these things in your program, all right? Now, where it really depends. When you declare memory, what are you doing with it, right? If you are directly using it and then you're done with it, then you own the memory and you own the responsibility of cleaning it up, right? But when a function returns memory, right? For example, here, let's indent that. Let's go back over here to our examples over here. Remember that we did this ones array function where it created a brand new array and returned a pointer to that new array of size n. It does not own that memory because it returns it, right? We need to immediately return it. If I were to free that up here, free the result, right? If I were to free that up before I gave it back to you, would that work? No, you asked me to create something, I created it, and then I immediately destroy it before giving it back to you, right? Well, what about freeing it up after I return it? That's dead code. That won't even be reachable. You return from the function, that's it. There's no code after that. So basically what this is doing is it's transferring ownership to the calling function, right? When a function receives memory, it does own it and it is responsible for it. Now what happens if it takes it and gives it to another function or gives it to another function? It really depends on what the transfer of ownership is, right? In general, all memory should be cleaned up, right? Except, of course, sort of is kind of, it's okay-ish to free it up in the not free it up in the main. Why? Because the main is the end of the program. The end of the program means that the operating system will take back everything that belonged to the program anyway, and so you don't really need to do it, but you will see what happens when you don't do it within the running of a program, right? You just keep grabbing memory, and leading to a memory leak, all right? All right. That goes into something a little bit more deep that we have to discuss here, right? So let's come up here and let's take a look at this code in main. I create an array of size 5, and I'm doing it dynamically. And then I go through and set it equal to 10, 20, 30, 40, 50, okay? And then I print it out just to make sure that it works, right? GCC, GCC demo, there we go, right? And let's go ahead and run that, there we go. 10, 20, 30, 40, 50. Remember that we made this fancy print array function before, right? We did that, right? Right? At least it's here. I don't know where it came from if we didn't do it. So let's go ahead and make a copy. I'm going to go ahead and call this BRR, right? Because ARR array, well, what's next? BRR. And I'm going to make it point to ARR, okay? Now I'm saying that this is a copy in quotations here, right? Because what is it really pointing to? So I've got a pointer on the left-hand side. Array, ARR, is a pointer. So these things match, right? Pointer, I'm setting that equal to a pointer. Let's find out what happens when I try to change something in, say, ARR, right? ARR sub 0 is equal to 42. Now let's go ahead and print them both out. Print array, ARR and N, and let's go ahead and print out BRR and N. What's your prediction here? Okay. Certainly, the first array is going to be changed to 42. So that'll be 42, 20, 30, 40, 50. But what about the second array? Right? It's also 42, 20, 30, 40, 50. Let's understand that by putting this into a visualization tool to see what's going on here. Okay? Let's visualize this. And, oops, okay, whatever. I don't need print array, but I'll go ahead and get rid of it and get rid of that. Get rid of that and get rid of that. Right. Let's just visualize the actual code that matters. Okay, there we go. So let's go ahead and step through this. All right, there. I've created an array of size 5, and I go through this for loop that sets it equal to 10, 20, 30, 40, 50. Right? Remember that it's allocated on the heap. Okay? Now let's make a copy. Right? BRR is a pointer to an integer, and it's a question mark right now because I haven't executed line 16. What's going to happen when I execute line 16? They point to the same array because they're both pointers. I'm pointing to the same thing. There's only one thing in memory there, see? Right? So they're pointing to the same thing. So now we understand why if I change A, why is it changed for B? Because they're pointing to the same thing. Right? A and B are references to the same array. That's not always what you want, but that is called a shallow copy. Right? And the opposite of shallow is a deep copy. Right? So a shallow copy is when two references, that is pointers, point to the same chunk in memory. Changes to one affect both, right? They affect the other, right? So there is only one thing in memory, right? Now, what you can have a deep copy of an array. Memory, there we go. All right. So you can have a deep copy of an array. That's the opposite of shallow, right? Why is it shallow? Because they're pointing to the same thing. It's not very deep, right? So let's go ahead and think about what a deep copy would be. It's just going to be the opposite. Changes to one do not affect the other. And why is this? Because there are two distinct things in memory, right? It's a clone, basically. We've cloned this thing so that whatever we do to the clone is not affecting the original. Now, how do we go about doing this? Let me come over here to Python Tutor, and let's go ahead and edit this code. And I don't want to make a shallow copy anymore. I want to make a deep copy. All right? So we will declare BRR, int star BRR is equal to, now I can't simply make it point to ARR. I need to make a completely new brand new copy, right, by calling malloc. Now malloc is going to allocate brand new memory over here so that we have two things in memory. Now I need to copy over each element, right? Because what's the contents of the second array as of line 17 right now? Who knows, right? Zeros, dead beef, whatever was there before. So for int I equals 0, I is less than n, I plus plus. I will copy over into BRR sub I the contents of ARR sub I. Now let's watch this as a visualization, right? Visualize this execution. And again, I don't have my print functions here, so we can't see that, but that's fine, right? Come on, there we go, finally. All right, so next. We've already seen this before. There's ARR, the first array, with 10, 20, 30, 40, 50. Right? And then BRR is going to be a brand new thing in memory. And I didn't do it here, but what if I set BRR of 1 to 42? Would that end up affecting ARR? Nope. So now I've got two completely distinct copies here. In fact, this seems like such a useful thing that you'd want to do it over and over again, right? Let's go ahead and put that into a function. Right? So let's come back over here to our demo, and let's go ahead and create a deep copy function. Right? This creates a new deep copy of the given integer array, returning the result. All right. Okay, so what should we call this first of all? Deep copy? Okay, that's fine. Right. Now I'm going to pass in the original array, so int star ARR, and what else do I need to pass in? It's length, its size, and in this case n. Right. Now, am I going to be making any changes to that array? No. So what can I slap in front of it to make a promise that I'm not going to change it? Yeah, const. Right, with a space. Right. Now, what's the return type here? Just one integer? Pointer to an integer. Okay. So let's go ahead, and I don't want to lose my. I wish there was a way to put two things on the clipboard, and with quick keys, but there's not, or maybe there is, and I just don't know what it is. Right? But so I had to copy paste that, and then copy paste that. Right, there we go. All right, this is what we did in the visualization tool. What I'm going to do is I'm going to rename this to copy, right, so that we don't get them mixed up. All right, I'm allocating enough space, right, the same amount of space that you told me that ARR takes. I go through and I copy over each one, and then I return the copy, and that's it. Right. Well, wait a second. What if you wanted this for doubles? Yeah, copy everything over, and it's basically the same function except that change every integer to double. And also, I wouldn't be able to call it deep copy anymore. I'd have to call it deep copy int and deep copy, and deep copy double, et cetera, right? So if you want a better solution, look up memcpy. What do you think that's short for? Mem copy, exactly. It is just a generic thing that I think that you have to set up the memory still, but you can go ahead and use memcpy to copy whatever's in this chunk of memory over to this chunk of memory. So it's not a full deep copy. You still have to do the first step of actually allocating something. Let's come up here and see if we can use this. Instead of making a copy, we'll go ahead and say deep copy of ARR sub n. And now that I've changed 42 in the first one, the second one should not be affected, and it is not. It's still 10, 20, 30, 40, 50. Right? A lot of the times you want a deep copy. You generally don't want shallow copies, right? Unless there's a good reason to do so, right? If you want to manipulate this data, that is change it, and also retain the original data, you definitely need to make a deep copy of the original data in order to change it. Otherwise, you lose the original. Okay. All right. Yeah, let's go multidimensional. No, actually, no. Let's do one more exercise here. So, exercise. Implement a function that filters an array and returns a new array containing only positive values. Right? There we go. So for example, suppose I had an array, say, I don't know, 5, 3, -1, 0, 4, -5, right? Then the output should be, what should it be? I'm going to retain 5, I'm going to retain 3, but do I retain -1? Not positive. What about 0? Is 0 positive or negative? Neither. Right? So we'll filter that out as well. And we'll end up with 4, but not -5 there. Okay? So that seems like a pretty easy function, but in C, it's deceptively complex, or deceptively, it is complex, right? So let's whiteboard this. How would you go about doing this? There's the original array. You want to create a brand new array of what size? In this case, 3. Do you know that it's going to be 3 every single time? No? So how are you going to be able to determine how big of an array it needs to be?
You'd have to count how many positives before you make them.
Go through it first, at least the first time, and count up the number of things that are in it that you're going to retain. Then you can create the memory. Then you're going to have to go through it a second time and copy over each one of those elements. Right? So it's kind of combining a couple of things that we've done so far, but we need to be a little bit more clever about it. Right? So let me go ahead and copy, say what this function is. All right? I don't know, get positives. Right, there we go. Returns a new array containing only the positive integers from the given array, right? Filtered, right? Zeros and negative values are filtered out. Right? This is actually quite a basic function of, or a basic operation of a lot of data analysis. You want to filter things out, and you want to return, retain only the things that you're worried or that you're concerned about, right? So get positives. I'll just immediately say that it's going to be, the return type there is going to be an array, so int star. We're definitely going to take an array and we're not going to make any changes to it, so const int star array, and we need to know what the size is. Do we need to know anything else? We'll come back to that, because as we go through this implementation, things are going to pop up. Right? This is why design is a back and forth kind of thing. I think I mentioned the MC Escher picture before of the hand writing the other hand, right? It's a continuous feedback loop. You design a function one way and then you start implementing it and you say, oh, like something came up, I need to redo this, or I need to change this a little bit, right? And so I'll leave that question mark there. All right, so get positives as your first suggestion. Let's go ahead and count up the number of positives, numpos, right? Okay, for int I equals 0, I is less than n, I plus plus. If array of I is strictly greater than 0, then numpos plus plus, right? Is there anything wrong with my first few lines here? Focus on line 105. What value does it have as of 106? Yeah. Garbage, dead beef, right? So what should it have? 0. There we go. There's also something else wrong in my first few lines. Yeah.
You haven't declared an output array?
Oh, okay. I haven't done that yet, but I will after I know how big it should be. All right. But before that even, what's the first thing you should do, or at least think about? Check for null. So more generally, error checking. Right? So check for null on this, check for bad values on that, et cetera, et cetera. I'll let you do that. Okay. Now I can declare an array. Int star result, say, I don't know, is equal to int star malloc size of int times, and now how many of them do you want? You don't want n, you want numpos, right? And eventually return it, result. I like to immediately have a return statement here after I've created the variable that I'm going to return, and then come back and fill in the blanks, just so that I remember that I have a return statement there. Now we need to go through it a second time. Go through a second time to copy over positives, ... So for int I equals 0, I is less than n, I plus plus. In fact, I could steal most of this code up here, right? That's what I'll do. There we go. If it's positive, then copy it over, ... So that's results of I is equal to array of I. Let's come back over to our example here. I is going to run on this first array, right? It's going to go 0, 1, 2, 3, 4, 5. By the time I get over here to 4, should I be copying it to index 4 over here? No. Yeah.
Do it to numpause.
Oh, okay. Well, numpause is going to be, say, 3. Maybe I don't want to change that.
You could create an array that's the same length, and then
Ah,
have numpause be like the index counter.
okay. So there's another way of doing this, right? What we did was we went through and counted up the number of positives. Then we're going to copy them over. What we could have done is we could have created this array that's just larger than what we need potentially. Then copy over things, everything over, and then what do we do with this wasted space over here? Well, what we could do is we could copy this over here, and then this temporary thing, we could delete that or free it up, right? So there are, as my high school algebra teacher said, there's more than one way to skin a cat, right? Up or down, right? And so we could do that here, right? He was an old guy. We don't, he never skinned a cat anyway, right? All right, so how do I copy this over? I certainly want another variable.
Maybe like an index counter.
Okay. What comes next? J. Where would you start your J? 0? Okay. And so results of J is equal to ARR sub I. Now, J's got to go up because J can't just be 0 forever. Once you've copied something over, though, J should be incremented. So where? J++. If you want to get really fancy, you could do something like that. I don't like that kind of style of programming, but whatever. Okay. Then return the result. All right. Let me take this example and see if it works. We've got everything up here in main. Great. Let's see. Int. Here's another quick and dirty way of creating an array that you can test stuff on. Sum array, right, is equal to, oops, there we go. And you need brackets there. But it will, the compiler will go through that and see that you've got a list there, count up the number that are there, and automatically have a size for it, which should be 6, right? All right. So now let's filter this out. Get positives of some array, and there are 6 things in there. And that returns a brand new array, pause. I'll just call it pause. Right. Now let's go ahead and print it out. Print array, pause. Uh-oh. Here's where that question mark comes into play. Do I know how big that resulting array is here in this code? Nope. What could I do? I could go through myself and say, okay, well, after you filter out all the negatives and zeros, then you should have 3 things over. Why am I duplicating work though? Right? The function has to do that. Why do I have to do that again? So what I need to do is I need to have 2 things returned. That's the array and then the size of the new array. Right? I want those 2 things returned. And if there's sort of language like, say, Python, you could tuple that up and return that. Right? I can't do that here. It would fail the vertical line test. You can't return more than one thing. But you can pass a variable by reference, a bucket. Int star size of result. Why would this help me? I'm giving you a pass by reference variable that you can change, right? You're the function now. You can change that to the size of the result. And then I can look at that function and say, okay, the size of the result must be 3. How would we do that down here? Pass that by reference, right? Once you've created it, once you've copied everything over, size of result should be equal to numpause. Right? What goes in front of that though? That's a pointer on the left-hand side, and it's a value on the right-hand side. So how do I make the pointer, this thing, into a regular old variable so I can set it? Yeah. Dereference it, which would be the star. There we go. Again, you just have to remember back and forth. Star or ampersand, star or ampersand. Now let's come up here to my main, and I'm not going to just pass in 6. I'm also going to pass in a new result here. I don't know, ampersand n or something. N. CCC. There. 5, 3, 4. It doesn't matter how many things I add now. -5, -5, -5, 6, 7, 8, 9. Right? The function does all the work for me. Right? Oops. Sorry, how big is it now? How many things did I add? 6, 7, 8, 9, 10, 11. How big is it? 3, 9, 12. Yeah, okay, there we go. All right. There. Is it getting them all? It looks like it to me. All right. So this goes into a design principle. Who's responsible for communicating what to whom, right? I could have done all the work myself up here, but then I wouldn't be writing a function. Or I could have done half the work myself and then made the function do the other half. Or I could have duplicated work. I don't like duplicating work. I don't like a messy who's responsible for what. I'm going to make this function responsible for everything, right? Because it does everything, right? All right. So that's a nice little function that basically combines everything that we've been doing up to this point. We have to pass in an array. We have to create a brand new array. We have to iterate over that array. We have to copy things over, but not exactly, right? And then we, of course, have to communicate a pass by reference variable back to the calling function. Right? So, nice. Right? Okay, that was our last exercise. Let's talk about multidimensional arrays. All right, there we go. Multidimensional arrays. So what do I mean by multidimensional? Well, a regular old array is only 1D, right? It's a one-dimensional array. Because you've got all these elements in this array, just like the number line, it's one-dimensional. By the way, what is zero-dimensional? A point, right? And then there's no such thing as negative dimensional. But you can have 2D arrays. We refer to them as having rows and columns. There are two other names for this thing. What's one name that you would say? Something that has rows and some columns, yeah? A matrix. Okay, so you're thinking mathematically, right? What if you weren't thinking mathematically? What if you were put on your business hat instead? A table or an Excel file, a spreadsheet. Spreadsheet, right? So tables have rows and columns, or you can call them matrices. Okay, it doesn't matter what you call them. Beyond that, you can have 2D arrays, 3D arrays, et cetera, but likely there's a better solution, right? 2D arrays make sense. We use those all the time. But 3D arrays, you're probably looking for some other solution, probably a structure. And we'll talk about structures towards the end of the semester, where you've got 5 pieces of data that you need to associate with one thing. Wrap that up into one structure and treat it as one thing. Okay? All right, in C, you can specify 2 indices. The ith row and jth column. We call that row major form because the row comes before the column. It doesn't matter, right? You can transpose this matrix. You can flip the table and look at it however you want to look at it. But we'll be looking at it with respect to row major form here. So the way that you set this up is that you need actually an array of pointers because each row is going to be a regular old array. Right? There are a couple of ways that you can do this, by the way. If you want to read more, you can read in the book. I've provided like 2 alternatives. In fact, in your lab this week, or maybe it's your hack this week, you'll be doing some image manipulation. And the way that the image manipulation library that we use works is it looks at this image as a table, right? You've got a bunch of rows of pixels and columns of pixels. But it doesn't actually store it that way in memory. What it does is it stores the first row of pixels and then the second row of pixels right after it, third row of pixels, etc. In other words, it just treats it as one-dimensional array. Right? And then it does all the math itself. Right? But we transform that so that it's more like this, where it's 2 dimensions. Okay? I think it's easier to think about in any case. All right, so let's come over here to the Python, this visualization tool, and let's go ahead and set up how we would actually do this. So I'm going to set this to be 3 rows and say 5 columns. Usually use n and m. You can use num rows, num cols, right? Or rows, columns, or something like that. Okay? So what we need to do is we need to initialize an array of not integers, but pointers, of integer pointers. Right? So int star star, do we want to call it a table or a matrix? Or do we want to have our business hats or our math hats? What?
So,
Table? Okay, your table. Matrix? I don't care. All right. Table. All right, table. There we go. Ooh. What's the difference there? A one-dimensional array has 1 star because it's a pointer, 1 pointer. But a 2-dimensional table has 2 stars because it is a pointer to an array of pointers. Right? So I will go ahead and write the rest of this. Malloc size of, we'll come back to that, times n. I want n rows, right? We initialize n pointers, 1 to each row, ... So now what's in each one of these rows? Well, not the rows itself, but we need not an integer, right? But we want an integer pointer. We'll understand this when it visualizes. Now what we'll do is we'll go into a for loop. For each row I, initialize the array for that row, ... For int I equals 0, I is less than n, I plus plus. Now here's where a regular old call to malloc is. Table sub I, that's the ith row, is going to be a call to malloc, and this is familiar now. Int star malloc, and each one of them is of size of an integer, but how many of them do you want here? If it's an n by m, yeah, m. There we go. There. Once you have that, you can treat it like a regular old 2-dimensional array. So let me steal this code right here so I don't have to retype it. Right? Oops. For int j equals 0, j is less than m, j plus plus. Right? We've got a nested for loop here. I'll say table sub I j is equal to I times j. You'll be doing something like that tomorrow. Right? You're doing a multiplication table. Right? So visualize this execution. Right? Come on, there we go. All right. So next, 3 by 5. That is a pointer not to an integer, but a pointer to an int star, a pointer to a pointer. And by the way, if you did ever want to do a 3-dimensional matrix, you'd follow the same pattern. 3 stars, and then it's a pointer to a pointer to a pointer. 4 stars for a 4-dimensional pointer to a pointer to a pointer to a pointer. Right? That's why we're not doing it. Right? There's the first one. It's an array of what? Integer pointers, exactly. On the first iteration, it will set up your first row. On the second iteration, it will set up your second row. And the last iteration, it'll set up that last row. Now, what about this thing right here? That's our array. That's our table. It's got 1, 2, 3 rows, 1, 2, 3, 4, 5 columns. Okay. After you've done that, you can go ahead and treat it like you would at, oh, this is not a I guess it is technically a multiplication table. It just starts at 0. Right, there we go. So figure out how to get the actual multiplication table tomorrow in your lab. Right? All right. So that's it, right? There we go. How do we clean this up once we're done with it? Yeah.
You gotta iterate through each of the arrays and free them.
Yep. So let's visualize this first, the wrong way of doing it. Let's just go ahead and free up that table. All right. I'm going to jump to, yeah, I don't want to pay you anything. Sorry, Philip. Philip Gow is the guy that wrote this. All right. Now he wants money. I'm not going to give him money. Anyway, there we go. All right, so we're about to free this table. But what does the table refer to? It refers to this array right here. What happens when we clean up that array? What about these 3 arrays down here? Did they get cleaned up? Not automatically, right? So what happens is, well, that first array got cleaned up. The other 3 are now a memory leak. And there is no way to access them because you've already freed up the pointers to them. All right, so your suggestion was we need to go through and clean up each row. Then and only then can we free up the table at the end. So free table sub I. Right. And visualize this. Right. Jump to the end and then I'll reverse it. Ignore it for a second here. There we go. Now here's the interesting part. I'm going to go through, and you can go in reverse technically if you want, but it doesn't matter. Forward or backward, doesn't matter. We'll free up that first row, goodbye, and there, it's dead, right? It's got a nice Halloween theme going there, right? That's actually, it's not Halloween, that's what it always is, but there's the second row gets cleaned up, the third row gets cleaned up, and then we can free up the table, right there. So the only proper way of doing this is you need to do each row. Now, the trick that I was talking about, the image manipulation library uses, where they have a first row, second row, third row, all in one contiguous thing. You don't have this issue because it's all just one-dimensional array. Right? But then you have to do all the math yourself. Right? So I'll make sure that you've got this in your notes. Right? And then let's take a look at Java really quick. See, there we go. So Java, there is no memory management. You don't have to clean anything up. But one thing that you might have to do eventually is 2-dimensional arrays. Int, what do we call it, table? There we go. 2 square brackets is equal to new table of 3 by 5. That's all you have to do. Oh, not table, but new integer. There we go. That's all you have to do to create a 2-dimensional array. Now this is an array, and before you remember what I told you, once you use lists, sets, and maps, you'll never want to go back. This is the one time you probably have to go back. Because if you wanted a 2-dimensional list, you could do it. You have a list of lists of integers. That gets really, really unwieldy. Right, there we go. I'll call this one the matrix. Right? Is equal to new array list. The problem here is now you have to go through and initialize each list. For int I equals 3 or 0, I is less than 3, I plus plus. Right? Now I have to go through and say that matrix.add new array list. There. Now it doesn't make it 5. I would have to add 5 things into it. Right, in order to do it, and so it gets really, really unwieldy really, really quickly here. So this is probably the one instance in which you'd probably want to use traditional arrays, right, for 2 dimensions. But then again, ask yourself, do I really need 2 dimensions here? Is there a better representation that I could use? But otherwise, for int I equals 0, I is less than, how do I know the number of rows there? I didn't put that into a variable, did I? Yeah, well, what was it with a regular old array? The array dot length, right? That'll get me the number of rows. Oh, what about the number of columns? So that I can set them. J is less than something, something. Table sub I dot length. No, yeah, no, that would be nice if there were width, right? But there's not. J plus plus. All I'm doing is I'm taking the ith row, and I'm asking how many columns are in that row. And so this one ends up being, table sub I j is equal to, I times j. There we go. All right. Now, to make sure that this works, I could write a print matrix function, or I could get us into what we're eventually going to be doing here, which is debugging. Come on, there we go. Actually, I don't want the breakpoint there. I think I've showed you how to do breakpoints before. I want the breakpoint right here. Done. There we go. I will set a breakpoint right here. And I will hit this bug up here, which automatically runs it And if you've set it up properly, or it'll ask you to switch to a debugging perspective. Right? Now that will run up to this breakpoint right here. Right? And what I can do is I can look at the table. Ah, there. 0, 0, 0, 0, 0, 0, 0, all the way to 4, just like the C version. And I can view this over here. I can view the matrix over here. And it's an array of, it's a list of lists, right? And I haven't put anything into each one of those lists, so it's different. It's empty. Right? But you can look at what arguments were passed in. Right? You'll note here that the program is running. It's just paused because I can actually terminate the program, or I can continue with the program by resuming up here. Resume, stop, step. Right? Step, and then it's done. We'll look into that much more detail later on, but I did want to remind you of that. Right? All right. What else do I have here? Oh, that's it. Okay. As a really quick exercise here then with the remainder of our time, let's do that filter function, that get positives. Where is it? In Java. But let's do it in a Java manner, right? I'm not going to use regular old integer arrays. Instead, I'm going to use public static void, or not void. What should I use to represent stuff now? I could do an integer array, but like I said, once you've used these other dynamic collections, you will never want to go back. So instead, what? A list? Now, if you use a list, then that tells me that you want to preserve the order. If I gave you 1, 2, 3, 4, 5, then you want to preserve 1, 2, 3, 4, 5. Do you care? If you do care, then this is the answer. If you don't care, then what's the answer? Set, right? Now, the other issue there is, what else is it about a set versus a list? What if it was 5, 5, 5, 5, 5? What would you get with a list, with a set now? Just 1, 5, right? So maybe we do care, and we'll go ahead and do it as a list here. All right. We'll take an input here. There we go. And here's the list, right? Input list, or whatever you want to call it. Now, I already erased the pass by reference variable that told you the calling function how big the result was. I don't need that here. Why? How do you get the size of a list? If I gave you a list, you could tell the size how? List dot size in this case. Length would be regular old arrays. Dot size would be for lists. Right? All right, we'll go through. Do I need to go through and count up the number of positives? No, because it's a dynamic list. All I have to do is add stuff, add stuff, add stuff. I don't need to go through it twice. Do I need to worry about copying things over to a particular index? No. Okay. So create a list here, integer, result is equal to new array list. Right? Oops, there we go. And then for each one, now do you want to use a traditional idiomatic for loop here in Java? Or you want to use that fancy thing, integer x in the collection list? All right. If x is greater than 0, then I don't need to copy it over. I just need to add it. There. Don't need to communicate that back to the calling function, and that's it. It's much simpler. Yeah. Oh, sorry. Thank you. Result.add. Thank you. Otherwise, I would have been screwing up your list. Oh, that's a good question, though. Right? I was able to screw up your list. Is const going to work in this case? Nope. There ain't no const in Java. Right? There are things called an unmodifiable list. So collections dot unmodifiable collection or unmodifiable list. There we go. I could give you this list, and then what it'll do is it'll give me a brand new list that is unmodifiable. The way that it does that is by simply overriding all the functions to throw an exception if you try to call them. And that's really not the way to do it, right? Unfortunately, that's because history in Java. That's just the way that they did it. Right? If you want a truly unmodifiable list, you don't want to go into the collections library. Right? All right. Any improvements on that? Other than, what else do you need? Documentation. Every function that you write now needs documentation. Use doc style comments for them all. Right? Just get into the habit. Right?
You need to check to see if it's null list.
Good question. What if it is null? When I iterate over it, what's going to happen? It'll end up causing a null pointer exception. So if I did my own error handling here, I would end up repeating what Java does for me anyway, right? That if I just let it go, it'll result in a null pointer exception and it'll throw it right back at you. So it's not necessary here. The only other thing would be like if you had a specific assumption about the contents of this list, that there were no zeros in it. Oh, you found a zero. Now we throw an exception. Right? Yeah,
Well, can't the list actually be null?
it could be.
Like, if list is
If list is null, then, but what would you end up doing here? Throw a new null pointer exception. Right? List cannot be null. Well, here, there. I don't care about typing. Right? I could throw it there, but Java will end up throwing it for me here. Right? And so I don't bother with those at all. Right? In fact, here's a preview of another trick here. We'll look at this when we start doing tooling. But you can set a breakpoint here. And then let's move over to our debugging perspective. What you can do is you can set breakpoints, but you can also set, how do you do it? I've got I can't see this anymore. There it is. There's that thing right there. So what I can do is, now I can set breakpoints at certain lines, but you can also set breakpoints conditioned on exceptions. So a null pointer exception, right? Now that's not going to occur on any particular line. That's going to occur anywhere in my program. If I want to debug this with respect to null pointer exceptions. So let me go ahead and call it down here. What was that? What was this called? Yeah, I guess I need a list of integers. Oh, here's another trick since we've got plenty of time. Not plenty of time, but integer foo is equal to lists dot as or of. There we go. Of 10, negative 40, negative 1, 4, and 7. There we go. There is a quick and dirty way of creating a list, right? List.of, and then it'll create with those contents right there. And then what did I call it up there? Get positives? Get positives of foo. That'll work perfectly fine. Great. But what if instead I passed in null? There's going to be a null pointer exception somewhere. Did I leave that? Yeah, it'll end up being right here at 33. And so when I run this through the debugger, it stops right there. What happened? It's highlighting this null pointer exception right here, in fact, right there. Null pointer exception happened right there. Okay, well, what variables am I looking at? Come on, refresh. All right, stop it and rerun it. There we go. There we go. What's null? Oh, list is null. Oh, okay. Right. You cannot call an iterator on a null list, and so that's why it's happening here. But it paused my program, right? Normally, what would happen if you were not debugging this? You would just get this output down here that it happened on that line. But with the debugger, you can pause it and look around. Well, what's null? What's the value of that thing? What's the value of that thing? And so we'll start looking at tooling here after after you get introduced to Valgrind tomorrow. Right. All right. So, any questions? No? Okay.